Hello and welcome back to EGR 171 Fluid Systems. In this unit, we're going to be looking at hydraulic fluid. The fact is, we use a number of different fluids in hydraulic systems, primarily oil, but we're going to look at the other types that are available, the properties associated, and some of the different tests and things like that that are done with hydraulic fluids.
So what do we want hydraulic fluid to do? Well, the fact is the primary thing we want it to do is to transmit energy or power. Fact is we put in energy through our prime mover to our pump, pressurize the fluid, provide flow that carries that energy through the system and then does work at the other end. To do this, we of course want the fluid to flow easily with minimal resistance or friction, and we want to make sure that any pressure we put in at one point carries through it relatively quickly. So this is something that's pretty common to most fluids. So what other kind of things would we like our fluid to do for us? Well, one of the main benefits of, particularly of hydraulic oils, is that they provide lubrication. The fact is, all of our components are essentially bathed in this fluid. So it actually provides the seals and the lubrication for the devices. So we reduce friction, and as a result, the components have longer life in that they wear less. In addition, we want to prevent our components from rusting. Fact is, most hydraulic components are steel, and steel does rust. So hydraulic fluid will hopefully help to prevent that. In addition, we want it to carry away contaminants and in certain situations, we want it actually to take heat away as well, right? We want it to be an effective media for taking heat from the components and getting it out to the environment to maintain the fluid and the components at a desired temperature. So let's discuss these various desirable characteristics for our hydraulic fluid. One of the key things is this issue of lubrication. Fact is, when you look at a surface, even though it may appear very smooth, under a microscope, you'll see that there are significant irregularities. You can see it here in a journal bearing and the bore. And what we would like our fluid to do is essentially fill these irregularities and allow for smoother motion. Right. The key thing about this is we want to reduce friction, right? That's lost energy. And of course, we want it to reduce wear. Of course, we don't want our devices to wear out. We want them to have a long service life. So that's one of the key things we want our hydraulic fluid to have, is this lubricating power. Another important characteristic is this flowability, or if you think of the opposite, the resistance to flow. It turns out that viscosity is how we measure this resistance. Essentially, it is how thick a material is. If we have a very high viscosity, that means it's not going to flow particularly well, say something like maple syrup. On the other hand, if you have a low viscosity, it's going to flow more easily. Water, for example, has a very low viscosity. Now, keep in mind a couple different things. We don't want it to have either a very high viscosity or a very low viscosity. We want it to have actually a very specific range of viscosity. We want to, of course, have a high enough viscosity to provide the lubrication, and we want to have a low enough viscosity for it to flow easily. Now, keep in mind when we think about viscosity, we tend to confuse it oftentimes with density. We think of a thick material as a dense material, but keep in mind when we're dealing with, say, water and oil, oil has a very high viscosity, but it's not nearly as dense as water. Water is actually about a third heavier, but has a much lower viscosity. So they are independent of each other, and that's an important thing to keep in mind. Another aspect of viscosity that we need to consider is its overall stability. The fact is, we want our device to function with a set stability level, and in most cases, we prefer it does not change dramatically during operation. Two things that potentially could change it are temperature and pressure. Most oils in particular are highly dependent upon temperature. The fact is, as the temperature goes up, the viscosity goes down. The oil flows much better. But of course, the trade-off is then you're going to lose its lubrication effects. Pressure has a somewhat similar effect in that as pressure goes up, viscosity goes up, but it's not nearly as dependent. As a result, we need a way to measure this change, and we use a property known as the viscosity index. We'll discuss this more, but this essentially is a measure of the rate of change of viscosity with temperature. Now, in most industrial environments, we keep our temperature and pressure at some pretty fixed levels. But if we're in a situation where we have a wide operating temperature range, for example, below you see a piece of construction equipment used outdoors, potentially in a northern climate, in that case, you may have very low temperatures that you need to maintain the viscosity in, meaning the fluid still has to flow even when it's very cold. There's a number of alternatives, things like oil heaters and stuff like that that can be used, but we want to make sure that given our application that our fluid is going to be functional at both the highest and lowest temperatures that we're going to see. Another characteristic that we're concerned with is the resistance to oxidation. Generally, when we think about oxidation, we tend to think about things rusting, metal rusting in particular, but keep in mind nearly all materials, and particularly organic material, will react with oxygen and it'll change its properties. Hydraulic fluid is primarily petroleum, and in this case it does react with oxygen, and that oxidation will cause a problem. The two things that tend to affect the oxidation rate are the exposure to oxygen, essentially the oxygen in air, and temperature. As temperature goes up, just like most chemical reactions, the speed of the oxidation is going to go up. In general, we're going to try to keep our hydraulic fluid in the range of 110 degrees to 140 degrees. The 110 degrees is about the minimum level we want for flowability, and the 140 degrees is about the maximum level we want for lubrication, but also to reduce the level of oxidation. Again, it goes up geometrically as temperature goes up. The other thing about it is we find that the oxidation rate is very dependent upon contamination. Things like water, metal fibers that might come from wear, any dust in the environment. These all act as catalysts to oxidation and cause the oil to break down that much quicker. So we want to minimize the exposure of those types of materials to prevent the oxidation rate from going up. Essentially, we want our oil to last as long as it possibly can. While we're going to minimize the exposure of our fluids to water, the fact is it's nearly unavoidable in most hydraulic systems. Generally, we have open reservoirs, and it does interact with the environment. Fact is, even very dry air has some level of humidity in it, and when that air is exposed to heated and cooled fluids, it can condense into water and potentially mix with the fluid. This is a problem for a variety of reasons. One, water, of course, is not a very good lubricant, so that potentially is an issue. It could also promote oxidation of both the equipment and the oil. And as a result, we want to prevent that from happening, or at least have a maintenance plan for dealing with it. One of the ways we do this is using petroleum. Fact is, petroleum and water and oil do not mix, as they say. And the way to say that scientifically is it resists emulsion. And this allows us to actually separate out the water. And it's one of the functions we'll see of our reservoir, that when the oil and any type of water is in it, it's going to settle to the bottom of a reservoir. Keep in mind, we also have a number of water-based fluids that are used in hydraulics. You may think, well, then why would additional water be a problem? Well, the fact is that water is going to change the properties. It probably will have an effect on viscosity. It definitely may have an effect on wear. So when we even have water-based fluids, we want to keep the percentage of water consistent. Now, a common problem with any type of mixing of fluids is foaming. The big issue, of course, with foaming is that it traps air in air bubbles. This is referred to as entrained air. We want to make sure that we don't pull that air into the piece of equipment. We talked about that a little bit with pumps, issues of contamination, but also major concerns with cavitation. Keep in mind foam. Again, you're exposing the oil to all that air and oxygen in the foam. If this is drawn in, that potentially is going to affect your operation. You're going to have air in the lines, which is problematic. So that's a concern. And keep in mind, as that oxidation occurs, you will eventually get a sludgy material that is very problematic. It's thick and it's significant problems in terms of the performance of the equipment, providing a lot of issues with friction and potentially wear. And of course, it's going to reduce the service life of the oil and potentially the service life of your equipment. So I want to make sure that foaming is prevented as much as possible in our hydraulic fluid. Another characteristic of hydraulic fluids that we need to consider is it's resistant to fire, either high temperature or flame. The fact is there's a number of different temperatures that we need to consider. It's also important to realize that the most common type of hydraulic fluid we use is petroleum-based, which is clearly flammable. If we look at the flash point is the lowest temperature at which the vapors are going to ignite. It turns out that anytime you have a liquid, there's a certain amount of vapor that is consistently going to be coming off of that. It's going to be vaporizing. That's what evaporation is. It's that oil or any liquid converting over to vapors. So in general, even in a hydraulic fluid that's we're trying to be careful with, there's going to be a certain amount of vapor, particularly in any kind of open container with it. In those situations, the flash point is the lowest temperature at which those vapors will ignite, but you need exposure of flame. And it's called the flash point because in general, the vapors will ignite and burn off, and then the fire would go out. On the other hand, if you continue to raise the temperature, eventually you're going to get to the fire point. The fire point in this case is if it's exposed to an open flame, it will not only ignite the vapors, but it will actually ignite the liquid as well, and it will continue to burn. So flash point is the lower temperature, fire point higher temperature, and eventually we'll reach the spontaneous ignition temperature. And this is essentially when the oil will just ignite on its own. If you get fluid hot enough, it'll just burst into flames. So we want to make sure we avoid that. Generally, we're going to work, of course, if you keep it below the flash point, then you won't have to worry about these other two, but you should realize that there are some differences. And keep in mind, just solving the problem of not exposing a system to open flame solves most of the problems, but you still have to be careful about how hot oil or other materials for that matter get before they could spontaneously ignite. As I've been saying, the most commonly used fluids in hydraulic system are petroleum-based. Keep in mind they're going to be the petroleum oil, but they are going to have a wide variety of additives as well, which we will discuss later in this chapter. Why we use oil is because it has all of the properties we want. It has very good flowability, especially at elevated temperatures. It's a decent lubricant, and it has a long operating life, so it doesn't break down or doesn't oxidize. Eventually it does, but it lasts for a very long time, particularly if treated well. It tends not to foam, which is another big problem, and it's not so thick that contaminants are trapped in it. If you leave oil in the reservoir for a period of time, the contaminants will separate out and oftentimes settle to the bottom of the reservoir for eventual removal. One of the problems with oil, however, it is potentially toxic and not particularly good for the environment. As a result, if we have situations where we might be externally outside working with something that we want to avoid a spill with, or might be working in the food processing industry, we may want to work with biodegradable fluids that eventually will break down and be non-toxic. So we have a number of different environmentally safe ones. And if a large spill does occur, still needs to be cleaned up. We can't just let it just break down on its own. But if a little bit of residue is left over, it won't be a major problem. A number of these are made out of vegetable oils. We also use synthetic ester-based oils that will break down with exposure to air and the environment. Now, one of the other problems with oil is it's relatively expensive. So as a result, if you have a very large component, for example, in this case here, we have a large hydraulic ram over here, we may want to essentially stretch our oil out. And we can have a number of systems that actually use primarily water with a little bit of oil in it to still provide the lubrication. Fact is, water is almost incompressible. So even with that small amount of oil, it'll still function at a high pressure, up to about 3,000 psi. Now, the one key thing about water is its temperature range. Below, for example, 32 degrees Fahrenheit is problematic, and if it ever gets closer to its boiling point, that's problematic. So when we're dealing with these soluble oil emulsions, we want to make sure that we definitely avoid freezing. Keep in mind one particular issue with that is if it does freeze, it tends to separate the water and oil out, which is very problematic. And then, of course, we don't want it to exceed, usually set around 140 degrees Fahrenheit, because much above that, we're going to have a lot of evaporation. And the fact is the water vapor is going to come off, and we're going to lose a significant volume of our hydraulic fluid. In situations where exposure to open flame is unavoidable, or we may be dealing with very high temperatures, we may want to choose to use one of the fire-resistant fluids we have available. For example, that water and oil emulsion that we talked about is resistant to fire as long as it contains about 40% of water in the oil base. Still has most of the properties of the oil, but that water will prevent it from give it a significant resistance to fire. We can also use water and glycol. Glycol is, of course, the material found in antifreeze. It has a very thick film similar to oil. And in those cases, we can use anywhere from about 35 to 50% water to resist fire and still have some of the lubrication effects that oil has. There are a variety of different synthetic fluids out there made with things like esters and hydrocarbons that are designed to resist fire as well. We can do this with certain additives and in general, it's going to have a number of the different desired factors that we want, but keep in mind synthetic fluids are significantly more expensive, and oftentimes, if you can avoid it, you try to work with your standard hydraulic fluids because all of these have trade-offs. They're definitely not as functional as hydraulic fluid, petroleum-based hydraulic fluid. As I mentioned, fluid manufacturers tend to add a number of different agents to change the properties of our hydraulic fluid. In most cases, the idea is to prevent some sort of negative thing from occurring, and these agents are specifically designed to address them. So for example, if we have a situation where we have very high levels of pressure, we have what are referred to as extreme pressure agents. They're designed to stay between the metal to metal and prevent contact and wear. We also have specific anti-wear agents that are designed for low operating pressure and temperatures. Right? So when our viscosity might be particularly high, again, designed to prevent wear. Oftentimes, these are agents that actually bond to the metal surfaces, so are on those surfaces regardless of the presence of the oil. In addition, of course, we don't want our systems to break down. So to prevent our oil from breaking down, we use an oxidation inhibitor. Keep in mind, as oil gets oxidized, it tends to get thicker in the form of sludges. If exposed to very high temperature, it actually forms varnishes. And you may have seen this on any type of equipment where you've overheated it, where it's that brownish film that's stuck to the surface. It definitely happens in cooking pans where you cook in oil, that those varnishes occur. Keep in mind, we do also want our equipment to prevent rust of the actual components. So we use rust inhibitors. These form a film on the metal, but also neutralize acids that will catalyze in terms of expanding the oxidation process and the growth of rust on our various components. As you can see, hydraulic fluids are relatively complex. They have a wide variety of properties that you need to evaluate if you're trying to select among the various choices available. Keep in mind, one of the simplest ways to determine what would be the best fluid is to look at your components. Component manufacturers will include recommendations. Oftentimes, component manufacturers actually manufacture fluids as well, so they would generally recommend their own types of fluid. But you can look at all the fluids available, and you're trying to match your requirements to what the fluid has for characteristics. So look for similar terminology in terms of how the fluid and your needs are described. You definitely want your test procedures to match up with the manufacturer's test procedures, so you're comparing apples to apples, and of course make sure you're comfortable with the units of measure. Fact is, different fluids will be described in somewhat different ways, so converting back and forth can be problematic, so a consistent use of various units is helpful. One of the more complicated properties to evaluate is a fluid's viscosity. And the complication comes from the fact that it turns out we have multiple viscosity measurements. And in fact, they measure things that are somewhat different from each other. For example, we look at the absolute viscosity. We're actually looking at how much force is required to slide one layer of the material over another. We actually use a multi-plate system with the fluid in between in terms of measuring the force. This isn't necessarily the most precise way of actually determining the viscosity, at least as far as what we need for hydraulics, however. In general, what's recommended is the kinematic viscosity. In this case, we're looking more about the level of flow. The mechanism you can see here on the right, we actually put fluid into our system. We obviously want to control the temperature. As I said, viscosity is very dependent upon temperature. And we want to look at how long it takes for the flow to move through a given system. This gives us a more precise indication of the viscosity that we're going to see in a hydraulic system. This is generally the measure that you'd like to see, but not all manufacturers use it. So keep in mind you need to be careful about the viscosity measurements you find associated with your fluids. The good news is you're rarely going to have to measure viscosity unless you work for an oil company. In most hydraulic situations, you'll be purchasing oils based on a standard viscosity grade. There's actually two different standards organizations that actually provide these. This includes ISO, the International Standards Organization, and SAE, the Society of Automotive Engineers. ISO has 20 grades, and they base their grade on the viscosity at 40 degrees C. Keep in mind that's a limited number of grades, and as a result there can be some significant variability, but that 40-degree temperature is relatively close to what our operating temperature is going to be for our hydraulic system, so there's somewhat of a good matchup there. On the other hand, when we look at SAE, they have more grades, in this case up to 60, and they're going to base their viscosity at 100 degrees Celsius, which is closer to how automotive internal combustion engine temperature would be rather than hydraulics. So you need to take these issues into consideration when selecting which viscosity grade and which standards organization you're going to work with. The last of the viscosity measurements we want to discuss is the Sable Universal Viscosity. If you look here on the right, you'll see a Sable viscometer. And the way the device works is it's filled usually with water at a specific temperature. This is very common when measuring viscosity because, of course, viscosity changes with temperature, so we want to make sure the oil temperature is exactly at the amount we want. A valve is opened and the fluid flows out, and we measure the amount of time it takes for the fluid to flow through a very specific calibrated orifice at the bottom. This is not a viscosity measurement that's supported by SAE or ISO, in part because there's a lot of variability that could potentially happen with this. But it's a very simple test, so you're still going to see it widely used out in industry because it gives a decent measure of viscosity with a simple and inexpensive and relatively quick test. But you're not going to see it used in many specifications because it's not supported by the various standardized groups associated with fluid power. Another important aspect that we need to consider is how the viscosity is going to change. In this case, how it's going to change with temperature. We use a measure known as the viscosity index, or VI. This is something that is definitely going to be available in the specifications for any hydraulic fluid you purchase, and it's also associated with the ISO and SAE standards. What is a measure of is how much the viscosity is going to actually change between 40 degrees and 110 degrees C. The higher the number the viscosity index is, the lower it's going to change. So a high number means viscosity is very stable. When the system was originally developed, the most stable oil available was given a value of 100, and the least stable oil available was given a value of 0. Well, over time, lubrication science has had a number of different advancements, and as a result, we now have a number of oils that have a VI actually higher than 100. So that 0 to 100 limit is no longer in case. So you will see numbers over 100 for very stable oil. Now, just like all of these other things, we need a standard system for measuring them, and it's ASTM, the American Society for the Testing of Materials Standard 2270, that's actually used in determining the viscosity index. Two other closely related properties we need to understand are specific gravity and API gravity. Essentially, both of them compare the weight of a given volume of a substance, for example, hydraulic fluid, to an equal volume of distilled water. So essentially, it measures the relative density of our material compared to water. The fact is, specific gravity can be used for just about any material, but it's more commonly used with fluids. If you take a look here on the side, you can see for water, for example, our specific gravity would be at 1, right? If you compared water to water, it's going to be exactly 1. Now, the American Petroleum Institute, which is used with a variety of different petroleum products, has actually modified this somewhat, mostly for the fact that they prefer not to use decimals if it's avoidable. So the API gravity is just specific gravity times 10. So the API gravity for water, for example, is 10. This will give us a good indication of its relative density. The fact is we need to know density for a variety of different performance issues with hydraulics, the simplest one being just the weight of the system itself. Keep in mind, hydraulics is not only the weight of the devices, the components, etc. The weight of the fluid also needs to be taken into consideration. This is actually measured by a relatively simple device known as a hydrometer that actually will give you the specific gravity of the fluid. Now, let's talk about those temperatures we mentioned. The fact is, when we talk about pour point, the name is right, the name or the property that we're evaluating is right there in the name. It's essentially the lowest temperature at which the fluid will pour, right? Generally, this is going to be relatively cold, so we might have to use an ice bath, shown here on the right. And essentially, what we want to do is go to the point where the fluid will not move. And essentially, the pour point is defined as 3 degrees Celsius above this temperature. In terms of your actual pour point for your hydraulic system, however, you want to make sure that you select a fluid that has a pour point at least 20 degrees above your lowest expected temperature. The fact is, once you start getting very close to the pour point, the fluid gets extremely thick and essentially loses all functional flowability. One of the desirable properties we'll be looking for in our fluid is rust prevention. Essentially, any type where there's water going to be mixed with hydraulic oil, rusting can occur of any type of material that corrodes. Fact is, most of our hydraulic devices are going to be made of steel, which will generally rust. So we need to evaluate how effective the rust prevention is for a fluid, and we use a relatively simple criteria. Essentially, run the device for 24 hours in a standard environment, and essentially see if rust occurs. If no rust occurs, well, then the fluid passes. So this is pretty simple and straightforward. Now, we also want to look at the problems with corrosion and oxidation. The fact is, oil comes from petroleum, and crude oil oftentimes will have some sulfur in it. Fact is, sulfur will react with a number of metal components. So we do have a number of tests out there, standardized tests to check and see how that's going to occur. Again, we'd run the device for a period of time and test to see if any oxidation or corrosion has occurred. In addition, we want to make sure that our oil doesn't trap water or trap air. So we're going to look at its demulsibility and foaming characteristics. Demulsibility is the opposite of emulsibility. Demulsibility essentially is when we want the water and oil to separate, right? So that's something we would measure. In terms of foaming resistance, obviously the same type of turbulent mixing. We want to avoid foam occurring, and we want that foam to potentially break down relatively quickly. And it turns out that ASTM has a series of standardized test procedures available to evaluate each of these characteristics. ASTM has also developed standards for determining the lubrication and wear prevention characteristics of oil. For lubrication or lubricity, there's the Timken method. This uses a steel cup and a test block. It's going to be immersed in the fluid. A pressure is going to be applied, and we determine the maximum pressure before the cup and block actually damage each other. We also use this 4-ball method over here, where we have 3 stationary balls shown down here with a ball above. We have a load applied to it, and we're going to rotate that to determine how effective the lubrication is going to be in this environment. This is a standard way of measuring the lubrication potential for oil. One of the ways we measure wear prevention is to run a device over time. Most common device that suffers from wear is our pump. So we actually run it over a period of time, and we measure the weight before and after, and the amount of weight that's lost is the amount of wear. So we can evaluate wear prevention with that method. While it's essential to maintain your oil in proper condition while it's in your hydraulic circuit, we also need to be concerned with how we store our fluids and how they're handled. Fact is, this is a big opportunity for our fluids to be contaminated. So it's essential that it's stored in sealed drums. The drums are kept dry and clean. Drums are designed to be laid on their side. It's essential when you're transferring the fluid, filling the fluid, that the environment be clean, that you use proper filtration to avoid any type of contaminants getting in, right? So all that needs to be done. Not only keeps the fluid clean, but it also prevents it from evaporating or leaking, etc. Cleanliness is essential for proper hydraulic operation. The fact is, we are going to use our hydraulic systems in a wide variety of environments, including, externally in construction sites and things like that. So we want to make sure we keep all that kind of dust and dirt out of the system as much as possible. But when you're in a contaminated environment, there is going to be a certain amount of it that will get get into your system regardless. As a result, you need to have a process in place to handle that. One way to do it is to prevent this from getting in is to keep the reservoir relatively sealed. Right? There's usually going to be a well-sealed environment where there is a vent, but that vent is going to have filters on it as well. One of the common places where contaminants come in, particularly with construction equipment, is where the cylinder extends and retracts. This is one of the few places where a component is going to be exposed to the environment and then taken internally. So we're going to have a number of different types of wiper seals on a cylinder, or if we're definitely going to be in a very dirty environment, we may want to use a boot of some type over the top of the cylinder that prevents that dirt from getting into the system. Of course, as I said, you can certainly limit it, but you still need to do regular maintenance and regular inspection to make sure that if anything does get in there, it doesn't build up to the point where it actually has a problem with your system's function. One of the key things you're going to have to maintain is the operating temperature. As we've indicated, we want our oil to be somewhere between 110 and 140 degrees Fahrenheit. This is generally going to be measured in the reservoir itself. And why we're so concerned about it is this temperature has got a lot to do with the service life of your fluid, but also the service life of your components. If you run your system at temperatures much below 110 degrees Fahrenheit, you're going to have a lot of friction and potential wear. Above 140 degrees Fahrenheit, you're going to lose lubrication. So we want to make sure we keep it within that range. A number of different things that you can potentially look into if you're having trouble maintaining that temperature, especially keeping the temperature below 140 degrees, is look at the temperature of the area that surrounds the system. If it's a hot environment, you may need to cool it off in some way, air conditioning, fans, etc. Keep in mind that the reservoir itself is designed to transfer heat, so you want to make sure that it is relatively clear and air movement occurs around the reservoir. The other thing about it is as dirt, dust, etc. builds up on the unit, that acts as insulation and prevents heat from transferring away from it as well. So all those things are things to be looked at if you are having trouble keeping the temperature down in your hydraulic system. Another important piece of equipment that functions in our temperature maintenance is the reservoir. While its main function is to store fluid, it's also designed to keep the fluid at the right temperature through heat exchange with the environment. We do this by having a reservoir 2 to 3 times the gallon per minute flow rate of a pump. This ensures that the fluid is going to be sitting in the reservoir at least 50% of the time and as much as close to 70% of the time. This gives us a chance for things like contaminants to settle out, but also a chance for the temperature to be regulated. Keep in mind this recommendation of the 2-3 times does depend on the system, however, and if you have systems that are very high volume, something like a large single acting cylinder, a large hydraulic ram, where a lot of fluid might be drawn into that component, you're going to need a larger reservoir. Other issues, of course, is the inlet and return lines. We want to make sure that we don't have turbulent mixing. We also want to make sure that we're not picking up any water or sludge that might be at the bottom of the system. And of course, there's all issues with the physical shape itself. We will talk more about this, but there's a number of different features built into reservoirs that improve its functionality. Lastly, I want to reiterate that fluid cleanliness and maintaining proper operating temperature are essential to the overall function of your hydraulic system and can't be overemphasized. Fact is, regardless of how careful we're about it, some level of contamination is going to get into your fluids, so a filtration device is going to be necessary, and maintaining that filtration device or filtration system is essential for the overall cleanliness of your material and the long-term functionality of your hydraulic equipment. If we're in a situation where temperatures are unable to be regulated solely through the reservoir, we can also add specialized heat exchanging devices that may heat the fluid up. For example, we talked about that in cold weather environments, or we may have coolers if we have a system that's going to be generating a lot of heat. So we're going to have a wide variety of equipment out there. We're going to discuss more in future units that are specifically designed to maintaining those important properties of our hydraulic fluid. As always, if you have questions about any of this material, don't hesitate to get in touch with me. There's also a number of videos and additional material available on the course space that will help to further your knowledge of this important topic.